Hello, I'm Mike McCulloch. Today I'd like to talk to you about the equivalence principle, which is a common criticism of quantized inertia. The criticism is that quantized inertia violates the equivalence principle, specifically the weak equivalence principle that has been tested. So the usual way this is tested is very similar to Galileo's experiment, actually, of many hundreds of years ago, where he dropped two balls off the Tower of Pisa, and these two balls had different masses, and he found that they fell together, which violated what Aristotle had said. Aristotle said that larger objects fall more rapidly than smaller ones. And so the equivalence principle was established, and this was taken in much more seriously by Einstein when he was developing general relativity. And the equivalence principle is actually the basis for general relativity, hence the criticism of QI that it violates it. But I'm going to show you very simply that QI does not violate the equivalence principle, or at least the weak equivalence principle. So we could start by looking at an object which is accelerating, so the force on it, F equals ma, but let's say the force on it is also gravitational, so we have gmm over r squared here. So this could be the motion of a body falling in a gravitational field. In quantized inertia, little m in the F equals ma, the m in that equation, is slightly modified into m times a factor which is 1 minus 2c squared over a theta, where a is acceleration, theta is the cosmic diameter. So we can write this like this. And then if you multiply out the terms, you get this, the third line here, and then you can get this. So this shows that the acceleration of the object, of the falling ball, if you like, is given by a gm over r squared, which is simply the same as we had before, plus a term which is 2c squared over theta. And the interesting thing here is that the second extra term due to quantized inertia is independent of the mass. There's no mass in there. So that means that although quantized inertia makes objects accelerate downwards in a gravitational field slightly more quickly, so Galileo's two balls will fall slightly faster, it treats them all the same, no matter what their mass is. So the Galileo's two balls would still fall together to the ground, and so the weak equivalence principle is not contradicted at all by quantized inertia. Okay, so I hope you enjoyed this short, and I look forward to speaking to you tomorrow. Goodbye.